Hi, everybody. I'm a postdoctoral fellow at University of Laval. Started in June with Carl Guillemette, and I'm doing some work looking into the structural tectonic evolution of the Pontiac subprovince. I'm also starting off a block of presentations. The next 4 or 5 will be part of the Gold Fluid Window project, which is a thematic project under Metal Earth, of course. And the basic question of the Gold Fluid Window project is, where are these gold-bearing fluids coming from? At what PT conditions are they being generated? And the inspiration for this question came from work done by Ian Pitcairn and some of the people sitting in this room that showed that as you get to higher grades in these metasedimentary rocks, you see less and exponentially less gold contained in those rocks, suggesting that the gold is being released somehow. And that makes these metasedimentary rocks good candidates to be the source of this gold and perhaps even the fluids. So there's a lot of people involved in this project. Most of them are here. Most of them will follow me the next 4 or 5 talks. I hope I've represented your projects well in this list. You guys can correct the record if not. But as far as what I'm trying to do here, I'm just looking at trying to understand the different tectonic evolution of the Pontiac, and how that might have given rise to a structure or series of structures that could help channel these fluids to their final resting place in the deposits. So lots of people have worked, I should say a handful of people have worked on the Pontiac, on the structure of the Pontiac in the 90s, and then again sort of over the past decade. I'm just going to cite this work by Kemmerer and Berg because it's sort of similar in scope. They go as far south as we do, or as we did this past summer. And their overall interpretation of the structure of the Pontiac is that it's a series of 2 overprinting fold generations in upper nap that is thrusted at the storolite in Isograd over top of a lower nap that records a different structural history. It doesn't have that second deformation event. And so they have a recumbent F1 generation, as you can see depicted on the cross section here, and those are sort of overprinted by these upright to inclined F2s, giving this type 3 fold interference pattern, which you see there. So we went, and each of these green points here represents a place where we visited, collected rocks, collected measurements, and this is a summary of those measurements. So the north, medial, and south stereo plots here are of S0 or S1, so bedding or the initial foliation. And then we also have a stereo plot of S2. One thing to note with the bedding measurements is that as you progress from south to north, you see a progressive steepening of this S0 foliation. Things are quite shallow, down to about 20 to 30 degrees when you get as far south as possible. And then by the time you end up toward the northern boundary of the Larder Lake Cadillac-Break, things are nearly subvertical, with the exception of the western part of the study area where everything is quite shallow the entire time. By contrast, the S2, the crenulation cleavage is dominantly dipping northeast in most cases. So just to give you an idea of what structures I'm talking about when I say these different fold generations, and just a note for anybody who's more used to working in, say, the Abitibi, these are all sort of stepped back ones. So the D1 in the Pontiac is going to be what you're used to calling D2. So of course we have S0 bedding, which is just the fairly well-preserved bedding surfaces that we can still make out in the rock. And then generally there's an S1 schistosity that is related to these high-amplitude isoclines that have developed a biotite cleavage that is generally parallel to the bedding. So it's indistinguishable from bedding for most places except where you find hinges. And then we have an S2, the aforementioned crenulation cleavage, which you can see cross-cuts the bedding and the S1 cleavage at a fairly high angle, almost always dipping towards the north. And here you can see here that the S2 cleavage is generally developed preferentially in the metapolitic rocks, and it defines a sort of acute angle to the S1, S0 planes. And in thin section, we see that the S2 cleavage is sort of a disjunctive solution cleavage, particularly here, because we're pretty far north, and so it's probably forming under rather cold conditions. Again, just to show how the S2 cleavage preferentially develops in the politic beds, you can see that we have a generally north-dipping bedding surfaces that are tracked by the changes in lithology. And then you can see that the P-lights record a second cleavage that's oriented at an angle. It is often very subtly developed in the more Samitic gray wackies, but not always, suggesting that this isn't a case of cleavage refraction or something. It's probably truly related to strain partitioning. To address the what I mentioned off the top about the two different structural domains, it doesn't seem likely we were able to find rocks. This is actually a thin section from the sillimanite zone, but the best picture was by this big store-like grain, where we see a clear composite cleavage with S2 cleavage domain separating an earlier, probably S1 foliation. And again, this foliation quite consistently dips towards the north or northeast. Moving into talking about the folding generations, we were able to find some of these F1 closures. Like I said, they can be quite rare just because of how high amplitude they are. So they can be difficult to find, and it's these places where we see our S1 cleavage at quite high angles to our bedding surfaces. And here we have an example of this S1, or this F1 folding developed in a quartz vein, and then that is then overprinted by, again, north-dipping S2 cleavage planes with associated F2 folds visible on that oblique surface there. If these are so hard to find, how do people know they exist? Generally, they're inferred from flips in polarity of the quite well-developed bedding. So here are a few graded beds that are preserved in the lower grade northern end of the Pontiac. And so this is the dominant way of tracking these isoclines is by looking for changes in polarity. This is a normal north-dipping or north-younging polarity example here with sharp contacts between this more mud-rich bed and the return to the more Samitic material. Here's another example of these F1 folds that are folding the bedding surfaces, and as sort of a hint, again, note how low grade these rocks are, and as a hint towards where the talk is going, we regularly see these folds overprinted where we can make them out, overprinted by this S2 cleavage and creating these sort of hook and crescent or type 3 interference figures, like Kimmerer and Berg had originally pointed out. So this photo here was used in several publications from the Pontiac, and it's a quite famous sort of classic structure defining the Lac-Opsatica area. Very frequent South Virgin asymmetric folding that was previously used to support the interpretation that the entire region is constructed as on the basis of this top to the south thrusting. But these are non-unique in terms of what you can interpret them as, and they're in fact probably more useful to track your position within a larger fold structure. So not to direct the conversation too much, but if we picture, for example, a South Virgin sin form, like we would have here. So in this image, we're sort of looking to the east, as we are in this photo here that we recreated. Here we see that we have Z asymmetry, as we would expect on this shallow limb of such a sin form. And here, where we're now looking in the opposite direction, we see still shallow, but we have an S fold telling us that we are still probably on this shallow limb of a sin form. We see the same thing. Again, here we're actually looking east. So we're back to a Z fold geometry. And from here, I'm sort of going to try to convince you that these folds consistently record these two overprinting generations, this type 3 interference pattern, or close to type 3 interference pattern, and that they preserve this geometry quite consistently to trace out this sin form. So here we have a recumbent isoclinal fold, probably an F1, and that is overprinted by north dipping S2 cleavage planes related to these F2 folds, creating that hook and crescent interference pattern. Same thing over here, although here S2 is overprinting a more upright example of an F1 fold. And you can see each of the different sort of segments that we might find ourselves on that might lead us to convince ourselves that these F1 folds could be recumbent, because they probably are recumbent in these shallow dipping limbs of the F2 folds. Moving on to the steeper limb of the steeper portion, the northernmost portion, where we have, again, these north dipping axial planes, and then we see Z parasitic folds here where we're looking to the west, and same thing with this image that we just pulled back. That's another Z fold looking west, and then an S asymmetric parasitic fold here where we're looking to the east this time. So this all fits with the idea that the change in attitude of the Pontiac metasediments is tracking or tracing out this large-scale first-order sin form that is southward vergent, basically mimicking the structure that we see developed in that shallow limb, in the shallower limb near Lacopacetica. So here's a cut on the top of a surface that is showing both folds, and we get this nice interference pattern, partially due to the relief we see, and we get these sort of asymmetric egg shapes poking through that are one of the earlier axial planes showing through the complex folding. And I put the orientations of our supposed folds into visible geology, and we get something that, while not reproducing it perfectly, does show the same general geometry, suggesting that we're at least on the right track, and that this is the correct sort of two pairs of folds that we have developed in the Pontiac. Everyone's always interested in shear sense, so we consistently see the top to south shear sense that's always been reported throughout the Pontiac, except we've only ever noted it, we only saw it in the shallow limbs. So anywhere we had these shallow dipping Pontiac exposures, that's where we would normally see top to the south. We also have this nice sheared margin of this S-type dike here that gives us a good time constraint on or an indirect time constraint on the age of this deformation. And we don't see this on the steep limb. Steep limb, we normally see dextral shear sense, which might be related to later stages of deformation along the Larder Lake Cadillac fault. Okay, so just to summarize all of that, we do have an S2 that's developed throughout the northern Pontiac. It changes in its sort of character as you go from north to south, as deformation gets hotter. Our regional architecture, we've changed F1 from being recumbent to initially upright, although in the shallow limb of the refolded F2 fold, or the ultimate refold structure, you do end up with some of your isoclinal folds, your F1 folds, being recumbent. This produces a type 3 hook and crescent dominated interference figure with some contribution from other, because of the obliquity of the axial planes. It gives an intermediate figure with consistent top-south kinematics on the shallow limb, and we may have parasitic folds mapping a larger sin form. So if we put all of this together and make a schematic cross-section, we get this, which doesn't look too far off from what Adrian showed back in October for the Quetico. And it makes this nice sort of prediction of repeated flips in polarity, because we have these steep, numerous changes in Jungian direction on the isoclines in the steep limb of this F2 sin form. Whereas as we go south, we're consistently dipping shallowly. And so all that I would really say we're doing here is flipping the dependence from the folding is forming as a result of thrusting to the thrusting is perhaps related to folding. The folding is the major controlling structure of the Pontiac architecture. And if we extrapolate this a bit, and so noteworthy that a similar structure was proposed in the Granada Formation by Daigneault back in 2002, and we're just sort of extrapolating this into the Pontiac. And if we looked at the potential flexural flow we might expect if we have such a structure, if you'll grant me that the Pontiac might have this overall architecture, then what we'd expect to see is that top to south shear sense developed in the shallow limb, which we see, but we wouldn't get that in the steep limb, which we, as I said, don't have the field observation support. We don't see top to south shears maintained in that steep limb. Instead, we would expect more of a normal sense shear as the inner portions of the fold kind of, don't want to use the word extrude because it has other connotations, but that's sort of descriptively accurate. So extrude out of the center of the fold. So I don't want to spend too much time on this because Isaac's going to come in and tell you in more detail, but his recent paper, he showed that there's higher pressures recorded in the garnet zone than in the storolite zone, and the approximate locations of these isograds on this cross-section are shown here. Remember, this is where Camille thought the thrust was, because we have that change to dominantly shallow dipping structures, or dominantly shallow foliations and an apparent absence of S2. And this still holds pretty well here, and that the apparent structural positioning of the high pressure rocks over top of the lower pressure rocks, where you need about 6 kilometers of relative exhumation between the two, can probably be accommodated by this sort of flexural shear to bring those rocks up from closer to the core into levels that are at parity with these other zones, these higher grade storolite and sillimanite zones. And notably that's all happening around 2660 MA based on garnet lutetium hafnium chronology. And then just to sort of leave off on one possible consequence of this with respect to ore mineralizing fluids is if these fluids are being generated in the high grade rocks in the shallow limb, well, we now have either shearing or discrete shear zones that are shallowly dipping in that shallow limb that can conduct those fluids all the way north to where we have our steeper dipping limb. Then they have nowhere to go but up, and this is about where it intersects with the Larder Lake Cadillac deformation zone, where we know it's quite well mineralized. So that's all I got for you guys today. Thanks for listening.